Welcome to the Explainer. Today, we're going to get into the nitty-gritty of some of the most fundamental concepts in physics. And we're going to do it by breaking down a question from a GCSE paper all about nuclear radiation.
Okay, here's how we're going to tackle this. First up, we'll figure out exactly what an alpha particle is. Then we'll move on to balancing a nuclear equation, which is actually kind of fun. And we'll finish up by comparing two very different types of radiation risk. All right, let's jump right in. So let's start with part one of the question. This is all about getting to know the basic building blocks of one very specific type of radiation. The paper kicks off with a pretty direct question, just to test our fundamental knowledge of what these particles are made of. So what is it? Well, the key thing to remember is that there are actually two perfectly good ways to describe it. An alpha particle is made of two protons and two neutrons, which, if you think about it, is exactly the same as the nucleus of a helium atom. So either answer gets you the marks. Okay, now that we know what an alpha particle is, let's move on. Let's see how this knowledge helps us understand how atomic nuclei can actually change during decay. All right, the next question is a bit of a puzzle. We've got a nuclear decay equation here, but you'll notice there are a couple of numbers missing. Our job is to fill in the blanks. Now, to solve this, there's one golden rule you have to remember: conservation. Basically, the total mass number, that's the number on top, and the total atomic number, the one on the bottom, have to be the same before and after the reaction. They've got to balance. So let's break it down. First, what do we know about a beta particle? Well, it's got a mass number of 0 and an atomic number of -1. So to balance the top numbers, our missing number has to be 89, right? Because 89 equals 89 plus 0. Simple enough. Now for the bottom numbers. For it to balance, the number has to be 36, because 36 equals 37 plus a -1. And just like that, we get our final balanced equation for the beta decay of krypton-89. It's a really brilliant illustration of how it all works. And for the final part, the question shifts gears a little bit. It moves from the theoretical stuff to something much more practical, thinking about the real-world risks of being exposed to radiation. This is a longer one. It's asking us to compare two different scenarios, two different situations that both involve alpha radiation. Now, what's really interesting here is how it clearly separates these two ideas. The key difference, the thing that changes everything, is the location of that radioactive source. Is it inside your body or outside? So here's the crucial point. The properties of the alpha radiation itself are what explain this huge difference in risk. Think about it. Alpha particles are highly ionizing, meaning they're great at causing damage. But they have a really short range. They're actually stopped by your skin. So if the source is outside your body, irradiation, your skin acts like a shield, and there's very little risk. But if that source gets inside your body, that's contamination. All of that damaging energy gets deposited directly into your cells and organs, and that makes them extremely dangerous. And that really brings us to the main takeaway for this whole question. When it comes to alpha particles, it's all about location, location, location. And that wraps up our deep dive into this question. Pretty amazing, right? It just shows how physics gives us the tools to really understand and manage the unseen forces that are shaping our world all the time. Makes you wonder, what other unseen forces are out there shaping our daily lives?